So what direction do you want positive to be? Sure, okay. So if up is positive, and that initial velocity is up, then that is just going to be positive 15 meters per second. What else do we know is true for a ball being thrown through the air? If up is positive, then down is negative. Is there anything acting down? Gravity. The acceleration due to gravity, the whole time that this object is in the air, it is accelerating downwards at 9.8 meters per second squared. If up is positive, then we have to explicitly state that that acceleration is going to be negative. The acceleration is downwards. There's a part A here and a part B here. Part A says, what height does it reach? There is all sorts of things baked into that sentence right there. There's two pieces of information we can pull from there. What are they? What does the question, what height does it reach, tell you? Sorry? No, keep saying that. Is at the maximum height, the final velocity is 0. So when it's asking you the height that it reaches, that is going to tell you, the implication there is that it's telling you the final velocity is going to be 0. If the final velocity is not 0, you are not at the height. You're either still on the way up or you're on the way back down. Either way, you're not at that max point. And the other thing, the question, what height does it reach, is telling you is what you're looking for. What are you looking for? Yes, like you're 95% of the way there. We're not going to use distance, we're going to use, it's the other D word. Displacement. The vectored version. That's what we're trying to find. So once, and that's really the only kind of sort of special thing here with these kinds of questions. There's just, because you're told the object is thrown, there's an assumed acceleration. If they ask you what height does it reach, there's an assumed final velocity. But everything else, as far as the kinematics go, is exactly the same. If we have a VF, a VI, an A, and we're looking for D, what kinematic equation are we going to use? Yeah. You betcha. It's the same 4 kinematic equations. These, for an accelerating object. And based on the information that we have, this is the one that we're going to use. So now we just fill it in. VF is 0 and we're squaring it. VI is 15 and we're squaring it. Plus 2. A is negative 9.8 times D. And now we just have to go ahead and solve. 0 squared is 0. 15 squared is 225. Minus 2 times 9.8. 2 times 9 is 18. 2 times 8 is 1.6. So 2 times 9.8 is going to be 19 points. Negative 19.6D. We're going to subtract over the 225. And we're going to get that negative 225 equals negative 19.6D. Solving for D, we do what? Divide by negative 19.6. And we get that the displacement of our object is what? You all should have calculators, just so you can make sure you can actually do it yourself. 11.47, and that is a positive value. Negative divided by negative is positive. So what that's telling you is that the object has been displaced 11.47 meters. Which way? Sorry? Up. Which, if you think about the rest of the problem, it makes sense. It's being tossed vertically, so it ends up top. The minus signs in physics do a whole lot more than what they would have done in math. If this was just a math algebra question, there'd really be no real way to determine whether or not you screwed up a minus sign. If I give this question a question like this to my math 9s, for example, and they drop a minus sign here, they say negative 225 divided by positive 19.6, and they get a negative value down here. Outside of physics, there's no way to check this. But because this is a physics question, negative has meaning. We assigned positive to be up. If this final answer was negative, what would that mean? It means that the ball is below where it started. It's gone down. And if you look at the rest of the sentence that defines the question, ball's being thrown upwards. It should be above. And so now you've got all sorts of context to find some of those I dropped a minus sign kinds of mistakes. Because whether this thing is positive or negative have meaning. And going back and analyzing that's important. Okay, so that's part A. Let's take a look at part B. How long does the ball spend in the air? What is baked into that question? What are we looking for? Time. What time? Time to do what? So the 11.47 meters is the highest point the thing reaches. If you wanted to find the time for this, that would be, because the question says how long does the ball spend in the air? This, the time taken to get here, times 2. This is the top. If you found this time, that would be the time to the top. And what you want to do is you want to take the time to the top and you want to add it to the time going down. But presumably, it's going to land level to where it was thrown from. So your total time being equal to the time up plus the time down. If it's true that, I'll put a note here, if the ball is a ball, yes, if the ball is level when caught, I'll say it that way. So if the ball it's caught level to where it was thrown from, this is just the same as saying, I want the time to the top times 2. That's not always going to be the case. We'll do examples where the object's going to go up and then it's going to go all the way. Like you throw an object upwards from the top of a building and then it goes all the way down to the ground below. In those cases, this is not true. But here, because presumably you're standing on the ground, you huck the ball up, the ball's going to come back down, you're going to catch it. The time to the top and the time down are going to be the same. You find the time to the top, you multiply by 2. If you're going to do it that way, there's more than one way to do this. If you're going to do it that way, you can say, okay, well, I know the initial velocity. The initial velocity is positive 15. I know the acceleration because the object is thrown. The acceleration is due to gravity. It's negative 9.8 meters per second squared. Emma, when you calculated the 11.47, was it exactly 11.47 or did it keep going? It kept going. Okay, cool. So then we're not going to use this to solve this. But we do know that the velocity at the top is 0. And so if we figure out, because of the framing of the rest of the question, if we figure out how long it takes to get to the point where the velocity is 0, and then double that time, we'll find the whole time, all the way up, all the way down. So now I'm looking for time. I don't want to use the value that Emma calculated before because she rounded it. So using this information, what kinematic equation are we going to use? There are 4 of them. You betcha. If you don't have your formula sheet handy, I would encourage you to at least be able to reference it quickly. This one uses an initial velocity, uses a final velocity, uses an acceleration to find a time. So we can plug it in and solve. VF is 0, VI is 15, A is negative 9.8, and time is what we're looking for. This time is going to be the time to the top. So I'm going to explicitly put that in there. We're going to subtract 15. We're going to divide it by negative 9.8. And we're going to find that the time for the ball to get to the top of the arc is going to be what? What is negative 15 divided by negative 9.8? Can time be negative? So then your answer should be what? Positive 1.53. Thank you for demonstrating exactly the point I was trying to make a second ago. If this was a math class, there would be no functional way for you to tell whether or not negative 1.53 or positive 1.53 was the correct answer unless you caught your mistake here. But in physics, it's really easy. Are we allowed to have negative time? Can the ball go backwards in time to get to its high point? No. And that's what a negative sign would actually mean. Henry, wake up! I know it's after lunch and we're all tired. So this time here is the time it takes for the ball to get from where it was thrown to the top of the arc. What do we have to do now to find total time? Double it. Total time equals t-top times 2. So then total time is going to equal 1.53 times 2, 3.06. And that is the final answer to get to the top of the arc. That is not the only way to do this problem. But are we cool with the reasoning of how we marched it through? Questions, comments, concerns on what we've just done? Okay, if there's no questions, then I have a question. Don't flip the page yet. I have a question for you. On the and I've got some space over here. I'm just going to cram it in on the side. On the very first day, I talked about projectile motion. So for objects thrown, acceleration due to gravity, when we talked about objects being thrown into the air, there was a very important detail that I gave you for an object that goes up and comes back down. We said that the initial velocity was equal to the final velocity with a twist. How are the initial velocity and final velocity related for an object that goes up and comes back down and ends level? Brad, wake up. You can flip back. Presumably you wrote it down. For an object that's accelerating due to gravity that ends level where it started, Yuli, how are the initial and final velocities related? And the magnitudes are the same. So for an object that ends level with where it started, the initial velocity is equal to the negative of the final velocity. So there's another way we could have set up this exact same question. And I'm going to show it to you here real quick just to show you we get the same result. If you remember that this is true, we could say, okay, well, if the VI is equal to 15, then V final is going to equal what? Negative 15. The ball is level and on the way back down. The acceleration is going to be negative 9.8, because that's just gravity. And time is what we're looking for. If we use this instead, then this is going to give us the total time. It's going to go straight to the end. Because we're looking at the final velocity with the ball on the way down already. We're not using 0 for the top. We're using the negative of the initial to say that the ball is level to where it started. And I just want to show you that this equation gives us the exact same result. I'm going to cram it in here, and let's take a look. It's the exact same kinematic equation that Emma gave us a second ago. VF equals VI plus AT. VF is negative 15. That's going to equal positive 15 minus 9.8 T. Really tiny. It's crammed in there. Now, the mistake students make all the time here is that they're going to say that to get the t by itself, I want to bring this 15 over. What's negative 15? Oh, to bring the 15 over, what do I have to do? I have to subtract it over. So the mistake I see all the time is, what is negative 15 minus 15? Students will say that that's 0. It's not. What's negative 15 minus 15? Not 30. Negative 30. So we're going to get negative 30 equals negative 9.8 t. To get t by itself, I'm just going to divide negative 30 by negative 9.8. If you punch that into your calculator, what's the value you get? It sure as heck better be basically the same thing we found before. What do we get? What'd you get? Oh, you didn't do it. Okay. Someone punch it in. What do we get? We get 3.06. The value is the same. Two ways to tackle the exact same question. How you interpret the physics is what's going to change. Do I find the time to the top? If you do, then the velocity is 0, and then you can double it for the trip back down. Or do I go straight from beginning to end? Questions about either of these? Okay. Then when you're ready, flip the page. Okay, we've got a stone being dropped from a bridge. So let's draw this scenario. Here you are on a bridge. And over the edge, you're going to dump a stone. My daughter has this Winnie the Pooh book where in the river underneath the bridge, Eeyore is floating. Kind of, there's my attempt at drawing a donkey. He's floating on his back under the bridge. So let's pretend for a second that this is Winnie the Pooh. And Winnie the Pooh's solution to the problem is, let's just drop a really big rock. The wave will push Eeyore to the edge. Unfortunately, in the story, it doesn't. Well, it does, but it hits Eeyore first, and then Eeyore kind of pops up at the edge. But Eeyore definitely takes a rock to, we'll say, the stomach here. So let's assume that this is the children's book that I read to my sister. She loves this story. Oh, my daughter. She loves this story. A stone is dropped from the bridge onto Eeyore. It falls for 2.35 seconds before hitting the water. How high is the bridge? So what are the implications? Oh, first of all, I've drawn my picture. The very first thing you should decide is when you're defining everything going forward, what direction do you want to call positive? Alana, you want up to be positive still? Sure. Okay. As long as we're consistent now moving forward, we want to call up positive. Okay. If we do that, what do we know based on the wording of the problem? There's all sorts of meaning baked into all of these words. A stone is dropped from a bridge. What could you assume from that sentence? Language is important. Dropped is the important word. What does dropped tell you about? It's going down. It tells you something else. 0 initial velocity. If Winnie the Pooh hucked it at Eeyore, you'd have a non-zero initial velocity. Dropped means here it is, not moving, I let go. So this word right here, the implication here is that VI equals 0. You have 0 initial velocity. You're just going to let gravity take over and yank the rock down into your friend. In this case, your Pooh. Eeyore's down below. Okay. It's falling, so it's going down. Acceleration for a falling object is what? Because we called up, well, because Alana decided up was positive, acceleration is going to be negative 9.8 meters per second squared. What else do we know? is, we know the time is 2.35 seconds. And for the first part of the question, what we're looking for is how high is the bridge? So we're looking for the displacement. So let's plug it in and solve. What kinematic equation am I going to use if I'm looking for D and I know VI, A, and T? On the wrong side of it. There you go. What kinematic equation are we using? Which one doesn't use VF? There's only one. What did Ray Reed find? Cool. Yes, that is the one you're going to want to use. And this is a really nice equation to use. VI is 0, which means this is immediately gone. So now we can go ahead and fill in the rest of this. D is going to be equal to 1/2 times negative 9.8 times 2.35 squared. If you plug that into your calculator, what do you get? What'd you get? What's the next decimal? It's 0.60? Okay, cool. Okay, why is that negative? Bridges can't have negative height. What have you actually found? The distance what? Technically, that's true, but it's also not. What have we actually found here? D is displacement, right? Don't forget what these letters mean. What has been displaced? What's moving? This is not a trick question. In this problem, what's moving? The rock. So what you have found here, this is the distance, sorry, this is the displacement of the rock. The rock was dropped, Alana called up positive, so for the falling object, the displacement should be negative. It went down below where it started. So this makes a lot of sense. It doesn't make sense for you to say, oh, well, the height's negative 27, because that means the bridge is under the river. But as Kaylin said, this is actually also the height of the bridge because the rock was dropped from that. But it's important to make the distinction. What we've actually found is the displacement of the rock. The rock was dropped down. But this is equivalent to the height of the bridge equals 27.06 meters. But it's an important distinction to make that this isn't actually what you calculated. You calculated how far the rock went. They just happen to be the same thing. So in the story that I read my daughter, the bridge is not 27 meters high, so Eeyore doesn't, completely get annihilated. But let's say that it is 27.06 meters high. How fast is that rock going when Eeyore takes it to the gut? That's a good question to ask. So what we're looking for here is V final. What is the velocity as it hits the water? You're looking for the impact. And as much as possible, when you're doing a multi-step question, if you can avoid it, don't reuse values you've already calculated. You will introduce rounding error. And in this case, we can't avoid it. We can just go back and use this data right here. And instead of using this to find D, we can use this to find V final. If we're going to do that, we're going to use this kinematic equation. V final equals V initial plus AT. V final is what we're looking for. VI is 0. So this is just going to be negative 9.8 times 2.35. If you run that calculation, I'll do this one for you. You're going to get negative, I believe it's negative 23.1 meters per second. But that number doesn't mean a whole lot to us. So let's convert that into kilometers per hour to see how screwed Eeyore really is. How do I convert negative 23.1 meters per second into kilometers per hour? You bet. So what's 23? What is negative 23.1 times 3.6? It's going to be negative. It should be because that object is moving downwards. 23.1 times 3.6. Ezra, you got a number? So let's round that to 83. You betcha. That rock is moving rapidly when Winnie the Pooh drops it on Eeyore from 27 meters up. It's functionally equivalent to Eeyore getting hit by a bus traveling to Mission from Abbotsford. Which is way more entertaining when you think about it that way. Eeyore's gonna die. An important thing to know when you're trying to be funny and drop things on your friend. Okay. I've got one more for you. This example is going to require you to be really mindful of how you use the space available. I would like you to draw 3 lines, one all straight down, one from right at the edge, and one, where should we do it? Let's do it right here, from the B in before. We're going to set up the problem here on the left, and then I'm going to show you 2 ways to tackle this. And you, moving forward, you need to choose which of the ways that you want to adopt. I'll make the distinction between the 2 in a second. So, last example for today, and for before spring break, a ball is thrown vertically upwards from a 10-meter tall building with a velocity of 5 meters per second. How much time passes before the ball hits the ground? So you're standing on the edge of a building. Here I am at the edge of the building, and I huck the thing up. I don't catch it. It passes past me all the way down to the ground below. How long does that take? We could also figure out how fast it goes down, but the hard part of the problem is how long does this whole thing take? So let's draw what's happening here. We've got a building. Let's put it here-ish. There's your building. Here's you on top of the building. You're taking a rock and you're throwing the thing up. It's going to go up, and it's going to go all the way back down and impact right next to the base of the building. What do we know? Let's label the picture with as much detail as we can. What way do you want to call positive? Up positive? Okay. That wasn't supposed to sound as judgy as it did. Let's call up positive because that's what Ray Reid said to do. What else do we know? Let's fill in as much detail onto this picture as we can. I'll zoom in so you can see what I'm doing. The building is 10 meters tall. Good. Hey man, what's up? Sorry. No, you do what you gotta do. So that distance right there is 10 meters. Could be useful. What else do we know? Sorry? What velocity? But what is that? That is the initial upwards velocity of the object. Cool. So let's see if we can toss that in over here. We know that VI is equal to 5 meters per second. And as far as we know right now, that's it. Okay, so this is where I'm going to show you the two different ways to tackle a problem like this. Okay, so there's two, in physics like this, there's often multiple ways to solve a problem. This one is no exception, and the way you separate out the methods for solving these problems is that one of them, no, I don't want to use that pen. It's mushy. I want to use this pen. One way is going to have easy math. But there's always a trade. If the math is easier, something needs to be made to be more difficult. In this case, you can either have easy math and harder physics, or you can swap it. You can have harder math, easier physics. And it's always this trade. If you move to elegance in math, or if you want the easy physics route, the math will always be more intricate. If you want the easy math route, your understanding of the problem is going to have to be deeper. And again, I don't care which way you tackle these things. You need to pick a method that you're comfortable with and go for it. If math is not your strong suit, and yet you're sitting here in a physics class, this is not the way for you. The harder math, easy physics, is not going to work. Because there's tools and techniques that perhaps you've not seen yet, or you don't know how to use. So someone with an opinion, because Kai's not here, which one do you want me to do first? Based on just my description, how many of you think that you're probably going to take the easy math, harder physics route, just by show of hands? How many of you are like, screw that, I want the harder math? Okay, well that, you guys are in the minority. I'll show you both. You guys are in the minority. So we're going to do the harder physics, easier math first. Here you go. Here's how you set this up. If you're going to look at the easier math, harder physics, you have to break the problem up into two chunks. For the individual math pieces to be easier, you need to break them up into smaller chunks. And so what we're going to do is this. I'm going to take this problem and I'm going to split it right here. This is going to be part 1. This is going to be part 2 of the same problem. So the easy math, harder physics, the problem gets split into part 1 and part 2. Part 1 is from where the ball is thrown to right here. Why did I pick that spot right there? What is special about that point that I've labeled? Sorry? It's the peak. Why do we like the peak? What happened? Yes. Yes. Anywhere we can create zeros, that's going to make math easy. At the peak, the velocity is 0. So by setting this thing up into two problems, here's what you can say. For part 1, it's from where it was thrown to the top. We can say that the initial velocity is going to be 5. The final velocity is equal to 0. The acceleration is, because the way Reed set up was positive, the acceleration is going to be negative 9.8. And we're looking for the time it takes for the ball to make it from here to here. We're going to find that in a second, but let's set up part 2 right away. For part 2, we're looking at, okay, well, the ball went up. Now the ball's got to come back down. So part 1 is up, 2 is down. What is true about the ball from the peak to the bottom? What do we know? At the peak, how fast is the ball moving? 0. So for the path on the way down, now VI is going to be equal to 0. The acceleration is still going to equal negative 9.8 meters per second squared. But we've got another problem. If I'm looking for the time, I've left some space in there on purpose. If I'm looking for the time, we need one more piece of information. I need either the velocity that the ball hits the ground with, or I need to know how far this distance here is. Which one of those is going to be easier to find? Do you think? Given the fact that we already have a bit of displacement, or a bit of a distance right here. Jaden, you look like a man with thoughts. Different thoughts? Okay. Emma. We're going to find that distance here, and we're going to add it to the 10, so that gives us this whole distance here. So to do this portion, we need to find the distance to the top. We're going to add it to the 10, and that's going to give us this distance, displacement down here. Now, from the top to the bottom, this displacement is going to be negative, because the ball is moving from the peak to the bottom. So now we need to go ahead and find not only the time it takes to get to the top, but the distance traveled to get to that top. And now we've kind of got everything we need. Come on, Vine. And we can fill this out from here. So to find time first, it's easy to do. Using VI, VF, and A, we're just going to use this kinematic equation here. VF equals VI plus AT. VF is 0, VI is 5, A is negative 9.8, times time. For the sake of time, I will tell you that that value is 0.51 seconds. That is the time it takes the ball to get to the top of its path. So this guy here is T-top. We also need the displacement from here to here. So again, that's relatively easy to find as well. We're just going to use this kinematic equation. VF squared equals VI squared plus 2AD. VF is still 0. VI is 5, but we're going to square it, plus 2 times negative 9.8 D. 5 squared is going to be 25. I'm going to subtract it over. I'm going to divide that by 2. I'm going to divide it by negative 9.8. And you're going to find that that displacement is 1.28 meters. And this is the displacement to the top. And so now we know, for the second part of the problem, for the ball to go from the top to the bottom, it's going to have to be displaced how far? It went up 1.28 meters, so this whole displacement is what? 11.28, and because the ball is now falling, that's going to be negative. We added the displacement to the top to the 10 down. It's going to be negative 11.28 meters. And now we can go ahead and find the time. We're going to use D equals VIT plus 1/2 AT squared. It's the only one that doesn't use VF. VI is 0, so that's gone, which is great. So now negative 11.28 is going to equal 1/2 times negative 9.8 T squared. Again, as always, you got to be careful with the algebra. To solve this thing for t squared, the first thing you're going to do is take your negative 11.28 and you're going to multiply it by 2. Then you're going to divide that value by negative 9.8. Then you have to square root that value. When you do that, you're going to find that the time is 1.52 seconds. What time have we just found? What does this 1.52 represent? From when to when? From the absolute peak to the bottom. So this is peak to bottom. So then to find the total time, you have to add those two together. You're going to take your time from the top or to the top, 0.51. You're going to add it to the 1.52, and you're going to find that the total time is going to be 2.03 seconds. Believe it or not, this is the easier math, harder physics route. As far as the physics go, there's a lot more analyzing. You're breaking up the problem into two chunks. The math is easy. There's just also just a ton of it. But individually, the algebra is simple. Questions about what I've just done? Because I'm going to make this thing look a whole lot more gross here in a second. Okay. If you're into simplifying the math, this is the way you'll have to do it. You'll have to break it up. You'll say, okay, I know at the top the velocity is 0. And so you'll break it into everything that happens before that point and everything that happens after that point. 0 is going to simplify your life like crazy. For those of the 5 of you who put up your hand who wanted the more gross math, here's what you're going to face. Here we go. So we'll set it up the exact same way, except I'm not breaking up the problem. I'm still going to treat it like one big problem. And the physics is actually easier. We can say that the initial velocity is 5 meters per second. That's still true. I'm not breaking anything up. VI is right there. The acceleration, because we read at the very beginning called up positive, acceleration is negative 9.8 meters per second squared. The other piece of information we know is actually the displacement. If you recall, the definition for displacement way back on like day 2 of this chapter was that displacement is defined to be the change in position from the beginning to the end. It doesn't matter the path that gets taken in between. So then if you're going to do it this way, what's the displacement? How far is it from where the ball started to where the ball ended, ignoring the path the ball took in between? Yuli. It's negative 10. The ball was here. The ball ended here. Don't care about what happened in the middle. Displacement is negative 10. And now we can go ahead and find the time. The physics is way simpler in this case. The math gets way more interesting. Here we go. I can slide this over and I can work in this space now. Based on the information we're given, there's only one kinematic equation that's going to work. We don't have VF, so we're going to use D equals VIT plus 1/2 AT squared. Let's plug it in. Negative 10 is going to equal, VI now is not 0. VI is 5. So we're going to have negative 10 equals 5t plus 1/2 times negative 9.8 t squared. I'm going to clean this up a little bit here. We're going to get negative 10 equals 5t minus, I'm just multiplying the half and the negative 9.8. It's going to be negative 4.9 t squared. And now we want to solve this thing for t. But t shows up in 2 places. For students who have done Foundations or Pre-Calculus 11, what are we dealing with? a quadratic trinomial. And you've got a whole bunch of, if you've done pre-calc 11, you've got techniques for dealing with this. There are two of them. Either you're factoring this thing, or what other tool exists in mathematics to deal with an ugly beast like this? Sorry? I love how you said the formula, and we all know what you mean. The quadratic formula. Recall, the quadratic formula is this: x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now you're asking yourself, for those of you who have never seen this before, what the hell is that? Well, that is to solve equations that look like this. ax squared plus bx plus c equals 0, which we almost have. I'm just going to massage this thing a little bit here. I'm going to put everything onto one side, and in fact, I'm actually going to take these things, I'm going to move them to the left, because it's going to make this term positive. So we're going to get 4.9t squared. I added it over. I'm going to subtract over the 5t. Minus 10 equals 0. And now this looks an awful lot like this. Your a is going to equal 4.9. Your b is going to equal negative 5. Your c is equal to negative 10. And now you're not looking for x, because x isn't the variable that's being cubic or quadratic here, for lack of a better word. The variable is t. So what you're going to find is that t is going to be equal to the negative of negative 5 plus or minus the square root of negative 5 squared minus 4 times 4.9 times negative 10 all over 2 times 4.9. Now, if you've never seen the quadratic formula before, you don't need it. You have another method over here. Use it. But if you've seen the quadratic formula before, things like this are where it's actually practically useful. It's a fantastic tool to solve stuff like this. If you're going to use this method, I want you to practice solving this. I'll tell you what the values are that it should give you. When you run this thing through the quadratic formula, you're going to get t is going to equal either negative 1.01 or 2.03. The quadratic formula always spits out two values. One of these values we're going to throw away. Is time allowed to be negative? And see, this is the beauty of physics. Physics brings the real world into this. If this was just a question I gave to you in pre-calc 11, there's no reason why we couldn't keep both values. But here in physics, time is not allowed to be negative, so this one's gone, and you get the exact same value. Time is equal to the time it takes for a ball thrown upwards at 5 meters per second to end up 10 meters below where it started is 2.03 seconds. And the math there it's elegant. I wouldn't call this mathematically easy, but the physics is a lot less involved. You go from the problem to the end of the problem. The in-between, the math in between, is where things get gross, but don't blame that on the physics. That's the math. So, two ways to tackle the exact same problem. You need to pick, I'm going to give you practice now. You need to pick which way you're going to solve these things moving forward. If you've taken pre-calc 11, if you're confident in your mathematical abilities, there's no reason why you couldn't do it this way. If you doubt your math abilities at all, you've got to do it this yellow way over here. Are there any questions about anything I've just demonstrated? Okay. Then, flip the page. The rest of the class is for you to use however you would like. I would like all of you to attempt questions 1 through 8, using whichever methods make your heart the warmest. For those of you if you finished your lab and tackled these problems, and you're like, yeah, I feel pretty good about myself. I think I can do this no problem. Or let's say perhaps you saw this last year in Germany or Spain. I want you to tackle problems 9 and 10. The 9 and 10 are gross, but if you can do them, you can do anything. So rest of class is for you to do what you want. You can either work through your lab or you can tackle these sets of questions. Tomorrow's class is going to be very similar. And on Monday, March 31st, I'm going to give you a quiz on stuff that we've done up to this point, including these kinds of questions. Okay, time is yours. Go for it. Yeah, go for it. On your mark, it said giver. Good luck.